Today we're going to begin our unit on waves by talking about equilibrium, simple harmonic motion, and restoring forces. Remember that equilibrium is a position where an object is in a place where all the forces are balanced. The net force acting on an object is zero. Equilibrium is a place where objects want to be. In order to move something away from equilibrium, you have to put some energy into it. So you have to disturb an object or displace it. I have a small spring hanging from this pendulum clamp, and if I put a mass at the bottom of it, and I allow that force, right, gravity pulling on a mass is a force, if I allow that force to pull on the spring, it elongates the spring, it displaces the spring. But right now, the spring is in equilibrium. The mass is in equilibrium. The forces that are acting on it are equal and opposite. Gravity is pulling the mass down, and there's a restoring force on the spring, pulling it on the, from the spring, pulling the mass back upward. So it's in equilibrium. If we displace that, there's a force that wants to bring it back even. So if I pull it away from equilibrium and then let it go, then this begins to oscillate. And since I pulled it down away from the equilibrium point, there's a displacement, right? Remember Hooke's law, force equals K times X. So there's a displacement below that. If I let it go, it's pulled up to equilibrium, but then it has inertia. So it wants to keep on moving past that equilibrium spot, an equal distance above that spot, and then it will be pushed back down, and it continues to oscillate up and down. These oscillations are just repetitive motions. There's a couple of things that we can measure about this oscillation. One of the things that we can measure is how much time it takes for one oscillation to take place. The time for one full cycle. So no matter where you start and end this, if it starts at equilibrium and it goes down and back up again and then back to equilibrium, that will be one full cycle. Or if we pull it down to the bottom and we let it go, and it's going to go up and then come back down again all the way to the bottom, that would be one full cycle also. The time to do this is called the period of oscillation, and that's measured in seconds. But the other thing that we can measure about this is looking at how often this takes place. How many cycles are there every second? And that is called the frequency, how often something occurs. The number of cycles per second. And frequency is measured in hertz. There's a relationship between period and frequency. We say that these are reciprocals of each other. So not only do I want you to know what a period is and what a frequency is by definition. Period is time per cycle. That's an important thing to say, because frequently you're going to be given information about, a wave, 4 waves pass a certain point in a certain amount of time. And we got to sort out that information. So period, by definition, it's T. It is time per cycle, or eventually it'll be time per wave. This is measured in seconds. Frequency is cycles or waves per second. It's measured in 1/over seconds, or this unit of 1/over seconds is called hertz. So F is measured in hertz. This relationship between T and F is found in this reciprocal relationship. T is 1/F, and F is 1/T. They're inverses of each other. What does that mean? That means that if you have something that takes a long time to happen, then it doesn't happen very often. If the period is really big, the frequency is really small. Or if you have something that happens very, very quickly, it takes a very short period of time to happen, then it happens very, very often. You might find yourself at a railroad crossing counting the number of train cars that go by. And so you might say, well, in this amount of time, I counted 150 cars. Boy, you were stuck there for a while. But that is time that's the whole time that you have and the whole number of cars. And so from that, we could say if each car was a cycle or a wave, we could say, well, how many cars came by per second? So if you were there for, 10 minutes, then we might say, well, there was 150 cars in 10 minutes. So we would say 150 cars divided by 600 seconds. So cars per second is frequency. But if we said, well, how much time did it take for just one car? Well, then you would do 600 seconds divided by 150 cars. And that will give you the time per car, time per cycle. So big difference between period and frequency. They are definitely closely related, and one affects the other, but they are reciprocals of each other. So I want you to know the definition, and I want you to know how to calculate one if you have the other. Okay. So there's several check yourself questions throughout this set of notes, and I encourage you to take a look at them. But I want to also take you back to the fact that some things happen so fast that we're going to use some prefixes in front of the hertz. So both we might have things that take a long period of time or have a very short period, and so remember that we use kilo, mega, micro, nano, giga. All of these are prefixes that we can put in front of the standard unit of seconds or hertz. Seconds and hertz are not the same thing, but okay. So then there's some example problems that you can work your way through. I want to talk to you just a little bit about, we've said that something that exhibits this oscillating behavior has a classification of motion called simple harmonic motion. And so what would it look like? If you plotted a graph of displacement and time for something that was oscillating up and down, you would see that it would move at a maximum distance away, and then it would be at equilibrium, and then it would be the same distance away on the other side, like we might say a minimum distance away, and then back to equilibrium, and it continues to oscillate back and forth. Well, this creates sort of a sine wave or a cosine wave. So we say that these things are sinusoidal. An oscillation that can create a wave like that exhibits simple harmonic motion. And you'll see us refer to simple harmonic motion as SHM, simple harmonic motion. Okay, so these are things that can be described, whether it's a mass oscillating up and down on a spring, or you have a kid on a swing going back and forth. We talk about pendulums. Both of these will have a period and a frequency. They have a displacement, they have an equilibrium position, there's a force that restores them to bring them back to equilibrium. These are all the things that we'll take a look at when we talk about simple harmonic motion. So let's talk a little bit about restoring forces. Remember Hooke's law. You have a force on a spring, and then you're going to have a force that wants to bring that back to equilibrium. And so we said that each spring had a spring constant K, and that spring constant K was a proportionality constant depending on the type of materials that's used in the spring. But it was calculated as the force needed to stretch something divided by the displacement of the spring, and it's in newtons per meter. So force over stretch. If you had something moving horizontally, here they have an air track and a glider, and they have an equilibrium position, and they pull the glider away from equilibrium, a certain displacement. That spring wants to restore the force and pull it back to equilibrium. So the net force in an x direction here is negative k times x. Remember, the negative sign is because it's talking about the stretch and the force are in opposite directions. If you pull this a certain distance away, we've been talking about displacement as change in x, we could plot points on the graph moving back and forth, and you would see that there's a maximum distance that this object moves to the left and to the right. That is called the amplitude of swing. The amplitude is the maximum distance from equilibrium, and you will find that you have an amplitude on both sides of that equilibrium position. So wherever that object is going to kind of turn around and go back the other direction, the distance from that equilibrium position to that maximum displacement, that is your amplitude. So here they've graphed a positive and negative amplitude. Oscillation about an equilibrium position with a linear restoring force is always simple harmonic motion. Okay, and then the last thing I want to talk to you is kind of looking at a graph of position, velocity, and acceleration with relationship to time for an object that is oscillating, okay? This is a mass on a spring, very much like what we have here, and they have the object kind of compressed up away from equilibrium, and that's where they're starting. So it's starting at a maximum amplitude, it's starting at rest, so it has no velocity, and if we let go of this, it will have the biggest acceleration. And so I want you to see that as this moves from that maximum amplitude toward equilibrium, and then to the maximum amplitude on the other side, and then back to equilibrium, that you can see that the positions of the balls change, and then all of these graphs have the same shape, but they're shifted out of phase from each other. And that's because, it depends on whether you're talking about velocity or position or acceleration. So what I really want you to take a look at is what's going on with the object when it is at the maximum displacement in terms of its velocity and acceleration. When you're at that maximum displacement, whether it's at the bottom of its swing or at the top of its swing, the object is going to instantaneously stop. Okay, so our velocity is going to be 0, but it's going to turn around and go the other direction. Well, that's a big, big change. So the acceleration at those points will be the maximum value. And then when you swing through that equilibrium point, you've gone from rest to moving faster and faster and faster, swing through equilibrium, and then it keeps stretching, and so it's going to slow down, slow down, slow down. So when you get to equilibrium, at the equilibrium position, your velocity should be the maximum. And when your velocity is at a maximum, you're not accelerating. So your acceleration should be 0. So this is going to take you through these 6 positions through one full cycle. And you can see how does the position change, how does the velocity change, and how does the acceleration change. Okay, and once again, so please spend a little bit of time looking at that. Now, if you look at a position time graph that shapes out to be a cosine curve, we can describe the position time graph. The position of any object at a point in time is a function of the period and the frequency. So we say, we say the position is the amplitude times the cosine of 2 pi t over t, or 1 over t is f. So we can say it's there goes my crazy board again. We can say the position is a times the cosine of 2 pi times the frequency. So that's all I wanted to share with you up to this point. I want to encourage you to kind of spend some time on the graphics that the publisher has put in these notes, because that's set in there to make sure that you can understand what they're trying to say with the words. Okay, so analyze those diagrams real carefully and make sure that you understand the difference between period and frequency, how to calculate it, and then by definition and by formula. And then understand the difference between position, velocity, and acceleration for an object going through simple harmonic motion.